I know it has been a long day. So yeah, today I will talk about computer vision for autonomous driving. But before that, I would like to say a few words about my background, where I started from, and what actually brought me here. Then I will give some fundamentals of autonomous driving, and give some insights of computer vision, which is basically an essential module for the autonomous driving area. So I'm Greek, and I grew up on an island that is called Kalymnos, famous for natural sponges and climbing. Back then, I had no idea what engineering is, what programming is. I didn't even have a computer at home. But I loved maths, and I loved solving problems. So in 2002, I entered engineering school. I obtained my bachelor and master from electrical engineering department. Then I continued my studies in Lausanne, where I obtained a master from computer science department. I discovered my passion for computer vision. Thus, I moved to France for my PhD that was on 3D computer vision area. I joined later the computer vision and geometry group at ETH as a postdoc. I also worked for some time at IBM on computer vision application area, and since 2021, I'm actually a research scientist within the computer vision group at Huawei. So let's go now back to the technical part. Nowadays, there is a lot of development in autonomous driving systems. And we've seen many companies are actually working on the different levels of automation. There are, in general, 5 categories. The level 0, where we have no automation at all. There, the human driver basically performs all the driving tasks. Then we go to level 1, where we call it hands or feet off. The system, the driver, for this level, performs the driving tasks, but the system can control either vehicle speed or the steering under certain conditions. So let's say, for example, we are on a highway in a really sunny day. This level of automation can assist the driver. We go a bit more ambitious, and we have the level 2 that basically combines both functionalities, hands and feet off. For this level, the system basically can control both vehicle speed and steering. However, it's necessary to have a driver in the car, and the driver needs to be basically engaged with the driving and needs also to monitor the environment. Then we have the level 3, where we call it eyes off. For this level, the driver does not need to monitor the environment. But it needs to be able to take control when there is a notice. Later, the next basically level is level 4, where we call it minds off. At this point, basically the system can perform all the driving tasks, but under certain conditions. It might be possible that the driver needs to intervene in the whole control. And at the end, we have the level 5, where it's the full automation. Basically, there, the steering wheel is also like optional. The system takes control of everything under all conditions. So let's see now what we need for autonomous driving. Basically, we need to understand where we are. We need to have a map, and we need to localize ourselves in the map. Then we need to understand what is happening around us. Are there vehicles, how they are moving? Are there pedestrians crossing the street randomly, following the traffic rules or not? So as soon as we are we have localized ourselves in the map, and we have understood what is actually happening around us, we need to plan the path. And given this path, then we need to decide how we will move. Will we turn? We will accelerate? And at the last step, we need also to communicate, to say to the vehicle that you need to change the path. So for building all these modalities, we need sensors. And these sensors are mounted around the car. This is a list of the most common automotive sensors, and each of them has pros and cons. We use cameras in order to capture the visual information, the texture, the color. Cameras, however, do not perform well under extreme lighting conditions, weather conditions. Then, in order to understand the 3D world around us and not the 2D projection of the world through the cameras that we get, we use Lidar or radar. With Lidar, we have a more accurate 3D information of our world, and it does not, since it's an active sensor, it does not it's not affected by the lighting conditions, but it doesn't perform well during extreme weather conditions. However, the radar performs well in both cases, extreme lighting conditions and weather conditions. Then we need also to determine where we are, so we need satellite systems. We use also IMU to understand how the relative motion, basically, with respect to our starting point, how we have moved with respect to our starting point. And finally, we have new sensors, event cameras, that basically capture the brightness changes. And with these event cameras, we can capture changes, motion changes. So we basically make use of all these sensors. We fuse the output in order to build the whole navigation stack, and especially using camera and together with LiDAR and radar pipelines, we build the perception stack. In the perception stack, computer vision is one essential part. Given the camera feeds, basically, we can get outputs that allows us to understand what's happening around. So we can, basically, using images, we can understand, we can extract 3D bounding boxes of dynamic objects. We can then also extract semantic information. For example, which pixel belongs to which class. Is this a vegetation? Is this a vehicle? Is this a street? All this help us to understand our environment and be able to drive safely. Other attributes that we can get is, of course, related to the 3D space, because our world is 3D. So we can estimate the depth. We can compute how far away is an obstacle. And with this way, we can actually compute also the time that this obstacle needs to collide with us. And this is important information because we can actually avoid accidents with this kind of metrics. Another important attribute is also to understand how things are moving in the scene, not only how far away they are. So is this, for example, car driving towards us or to the opposite direction? Is it parked? So this information can be computed using optical flow. Basically, that is the projected 3D scene flow into the image space for the computer vision scientists here. So for all these computer vision tasks, the state of the art basically is deep learning-based pipelines. We get high performance for most of these tasks. However, there are still challenges and open problems. And with this video, I want to show you how challenging is the whole problem. So autonomous driving is a really interesting application for computer vision, because in the scene there are many extreme corner cases. Many events are taking place at the same time, and the system needs to be robust on these extreme cases. For example, here we will see at some point the motorbikes that do not follow the traffic rules and go on the right side of the car. Maybe in the beginning of this video, this will be repeated, there was another car that was coming towards us, and it didn't stop as it should have done, but turned left. Then we also see some basically pedestrians crossing randomly the street. So these are sudden events, corner cases, that the computer vision pipelines need to be able to perform well. So maybe at this point, yes, this is basically the example with the car that turned left. So indeed, it's a challenging scenario. We have sudden events, and we really need that the computer vision pipelines give us really fast output and precise output. Then we can actually build really fast, respond also fast, and avoid accidents like that in the videos, basically. Hopefully, yes, it was nothing happened. Another challenge is basically the variability in the driving environments. When we have networks trained on data that are taken from highways, we need these networks to perform also well on data that are taken from other driving environments. Roads with traffic jam, small roads from islands. So this is something we need to take care of. Finally, another basically important task is also the extreme lighting conditions and weather cases, changes in the weather. These are challenging use cases where most of the computer vision algorithms fail. I will show you some videos here that actually show exactly this. For example, here, during the direct lighting, the algorithm is not able to detect the car that is coming towards us. There is also another point where the algorithm also fails to detect the bounding box. Then another use case with the pedestrian with a red box, basically, because the pedestrian is in the shadow, it cannot be recognized. And also driving during night, this is kind of challenging because we have pedestrians on the sidewalk that are not visible, and thus the algorithm also is not capable of detecting. So the computer vision, there are still challenges that we need to solve. And just to sum up here, what I wanted to say is that the perception stack is basically the eye of the autonomous, of the self-driving vehicle. The computer vision is an essential part of this stack. In order now to tackle these challenging cases, we need to fuse different sensors, and we still need to build more robust algorithms. And indeed, the autonomous driving is a really exciting application area for computer vision. And there is a lot of research, basically, that we can do. And with that, I would like actually to thank you for attending this talk.